Hi everybody, my name is Patricia. I'm from the University of Maryland. Thank you for stopping by. Today I want to talk to you about my research titled Absorption Measurements of MGS1 and Other Martian Dust Signals. So to put it kind of simply, I wanted to kind of try and decode the Martian atmosphere using photoacoustic measurements of Martian dust signals. We live on planet Earth, however, there has always been growing interest in the habitability of other planets. Are there other places like this? Are there others like us? And one of the focal points of these extraterrestrial, studies is the planet Mars and the habitability of it. So when scientists talk about the habitability or possibility of life on Mars, that includes several different pillars. Some of them are formation, evolution, and geology of the planet. And what I'll be talking about today is the climate. What's it like? What's the air like on Mars? So the reason climate is important or of interest is because although Mars is pretty similar in the length of a day, the length of a year is pretty comparable to Earth, when it comes to the atmosphere, they're a little bit different. Martian atmosphere is about 100 times thinner or less dense than Earth. Its gas makeup is quite different. It's dominated by carbon dioxide. Additionally, Martian atmosphere is filled with dust. Dust is ubiquitous, especially with the lack of knowledge or understanding of other biogeochemical water cycles in Mars. Prevalence of dust particles in the atmosphere is increasing. It is pretty much the most prominent aerosol species in Martian atmosphere. I mentioned they're aerosols. Dusts are aerosols. It's a small solid particle suspended in the air. Why is that important to studying climate, you ask? Any particle suspended in the air can either absorb or scatter incoming radiation in all directions, and that can lead to a heating or cooling effect on the atmosphere. This is commonly known as the direct effect of aerosols. So studying dust on Earth is one thing. However, studying Martian dust is a whole other challenge. First of all, it's so far away. The bulk of available data comes from field measurements, and often in the field, we encounter unpredictable external factors that can affect our measurements. And since the bulk are field data, this is what is mainly put to feed computational model and gives us the Martian climate prediction as we have it right now. So just from that, there really is a need for lab-based measurements of these Martian dust properties under controlled conditions so that we can compare that with the field-based measurements to eventually get a better computational model and a better climate predictor for the Martian atmosphere. So that's where this project comes in. We in situ measured the optical properties, specifically absorption, of Martian dust simulants. Note that I said simulants because currently we don't have Martian dust available for research purposes. However, there have been a lot of scientists that have worked on developing these Martian dust mimics to see how they can compare with field measurements. I'll be focusing on the optical properties, particularly absorption. And when it comes to absorption, a common parameter that's used to compare one work to another, whether it's modeling, field measurement, or lab measurements, is what's called the imaginary refractive index. This is the part of the complex refractive index that describes the absorption properties of a particle. So I have highlighted here a figure from the Wolf paper in 2009. This is field collected data from the Compact Reconnaissance Imaging Spectrometer on board the Mars Reconnaissance Orbiter. So to kind of summarize this figure, they found out that the K values, K is the imaginary refractive index, They are negligibly small in the visible region, and the near IR, however, it increases quite steeply towards a shorter wavelength, and this is characteristic to the presence of an iron oxide. And a follow-up paper by Manago et al. In 2017 attempted to recreate what Wolf measured by fitting a few properties, which is the mixing state, mixing ratio, and refractive indices of silicate and hematite. Now, the reason they picked silicate and hematite is because they are believed to be the main constituents of Martian dust. And this is reflected in the samples of the Martian dust mimics we used in this project. We used 7 different Martian dusts we obtained from the Martian Garden and Exolith lab from the University of Central Florida. And what we did basically was we aerosolized this particles, which means we suspended it in air. And then we took a size distribution to see the size of our particles. And for the absorption measurements, we use what's called a photoacoustic spectrometer. The photoacoustic spectrometer gives us a direct measurement of absorption that we can convert to what's called the absorption cross-section. And from the absorption cross-section and the size distribution, we are able to get or retrieve the imaginary refractive index using P theory. And I'll show you our results for that. So this is the size distribution for MGS1, which is one of our Martian dust simulants. As you can see here, we have a mean size of about 1 micron, and this was pretty much uniform throughout all of our samples. And next, we have the absorption cross-section spectra. So we coupled this absorption cross-section spectra. You can see this, they're solid lines. We coupled it with the spectra of the imaginary refractive index, or K, which is the dotted line. So what I like to point out here first is that each sample does have its own spectral shape and at different size distributions, so coarse to fine. The absorption cross-section distribution does change. However, the imaginary refractive index is just a function of sample. It's not a function of size. It's an intrinsic property of the sample. What we see here, it does have some characteristics that the Wolf and Manago paper pointed out, which is a fairly negligible value of K, and it steeply increases at shorter wavelengths. Again, this was expected as our samples do have iron oxide as the main, I guess, chromophore or observer here. So next thing, we modeled something a little different. So instead of calculating and retrieving the imaginary refractive index, we took the refractive index that we measured for MGS1 as well as for pure hematite, and we varied size distributions going from 0.3 to 3.6 microns in diameter, and we wanted to see how the absorption cross-section would look. I want to direct you to the hematite one first. So the red line here is for 0.3 micron size of pure hematite, and the size increases towards the top. So as our size changes, we start to see a change in spectral shape as it turns more into a flat line. And the reason for this is with large size particles, especially highly absorbing particles like hematite, we see complete attenuation or a complete absorption of light at these wavelengths. Now, if we switch over to MGS1 at all sizes, first of all, we can see that the spectral shape doesn't quite change. And we can also see that it has kind of the properties of pure hematite at small sizes. So all the MGS1 spectra kind of looks like, or kind of mimics hematite at 0.3 microns. And what this tells us is the hematite inclusion is fairly small, that the spectral shape of MGS1 doesn't change as absorption isn't so extreme that it creates complete attenuation. So from all that, we know that to date, dust mimics are the best compounds to characterize Martian dust. And to the best of our knowledge, this is the first study to present values of directly measured absorption and imaginary refractive index of aerosolized Martian dust in ones. Hopefully, this can give way to a better metric in estimating climate of the planet. Hopefully, this can be used to feed into the models. Hopefully, this can be used to compare with field measurements. And as far as future work goes, possibly we would want to put in some mass-based measurements to directly measure mass-specific absorptions. Maybe even use a TM or an aerodynamic aerosol classifier to see the shape of individual particles, as well as maybe explore the cloud condensation or ice nucleation potentials. Like, could there be weathers in Mars? I think that would be pretty great. So just to end this presentation, I want to thank my advisors, Dr. Fuyasa Wuku, Dr. James Radney, and Dr. Christopher Zangmeister for helping me through this project, as well as the National Science Foundation for funding me and funding this research, and also to NOBCChE for organizing this virtual poster session. This is my first virtual poster session, and I'm enjoying it a lot. So this is just all great work. And lastly, I'd like to thank you for stopping by and checking out my poster. If you have any comments, concerns, questions, you can go ahead and email me. I'll be here, and I hope you enjoy the rest of your conference. Thanks. Bye.